There we go. So hello again, everyone. Once again, this is week 2 of the Summer of Bayes workshop series, and I think most of you saw of the teaching assistant for this course, Grant Billings. He was at the login session. He wasn't here last week, but he's here today, and I just want to point out that he's here to help out if you have questions regarding the technical setup, but also if you just want to ask a verbal question about some of the course material. I think he can help out with that as well. And I've set up a breakout room. You should all be able to see in your. I've set it to be open and that people can come and go from the breakout room whenever they want. So in your top menu bar, you should see a button called Rooms, and you should be able to go in and out of the help and troubleshooting room. Grant has it set up so that he's in the main meeting and the breakout room simultaneously, so he can yeah, if you have a question or need help, you can just go in there and he'll help you out, right? So yeah. And oh yeah, I didn't do a formal introduction, Grant, for you last time. Grant has been helping me out with these workshops for a couple of years now. He was a graduate student, now is a postdoc at NC State, working with Amanda Hulse-Kemp, who is ARS scientist in the genomics and bioinformatics research unit. And Grant also works on genomics and bioinformatics and works a lot on cotton, I guess, is your main crop of choice, right? So yeah, he's a big help, and we're happy to have him helping out with stuff. So yes, let's get started with the material. Oh, does anyone have any questions about anything from last week or any comments before we dive back in? Okay, so we did not, due to getting everyone on the same page last week and some technical issues, we didn't quite finish the material from last week, but I think it's important to cover it. So we're just going to spend the first little while finishing up last week's material from lesson 1 before we start lesson 2. So what I'd like to do is I will share screen, and then we'll go ahead and run the code up to the point where we left off. I'll give a little bit of review so you can remember what we were doing, and then we'll continue working through the slides and the code where we left off. So let me go ahead and do that. I'll share screen. There we go. Okay. And here, this is the workshop homepage. And we're going to be going back to the lesson 1 slides and resuming more or less where we left off. So if you remember what we had done, we had been working with a data set from an agronomic trial. And mostly we had been looking at a trial that was replicated at a bunch of different sites, and each site had multiple blocks with plots assigned to different treatments, incomplete blocks of different combinations of fertilizer, N, P, and K at different levels. What we had done was we had set up a statistical model with all the random effects, the site and block within site random effects. We'd sort of set up a model to capture the structure of the experimental design, and then we're sort of adding in treatment effects one by one to the model to build it up to the model we want. And we had gotten to the point where we had put a fixed effect, a treatment effect for nitrogen that, and then we were looking at, okay, what does our model predict in terms of at an average site, what would be the effect on yield of having no additional nitrogen versus 1 level, 2 level, and 3 levels of nitrogen. We were looking at the means of those. And because Bayesian analysis requires you to put priors, to have a prior assumption about the distribution of effects of parameters in your model. We had started to look at what happens when you go between having a completely flat prior on the fixed effect to having a reasonably uninformative normal prior centered at 0. So having half probability of a negative effect and half of a positive effect a priori, but no having a higher probability of effects near 0 because it's a bell curve. That's where we had been when we left off last time. So let's go, everyone, if you can, log into Series on Scinet, or if you're using your local machine. And I'm going to go ahead and start an RStudio server session, just like we did last week. So just these options should still be there from last time. If you used it last time, we're going to still use the SEA stats training account in the series Q R 4.4.1.
Yeah. Oh.
4 hours, 4 cores. Someone is not mute. Okay, there you go. Thanks. 4 hours, 4 cores, and 16 gigs of RAM. And you can use this -- reservation equals Bayes 2025 to expedite its starting. Yes, thank you, Grant, for posting that in the chat. A link to where all this is also written if you fall behind. So I'll start my session.
Hey, Quinn, I have a question about this, starting your sessions. If I go to my interactive sessions,
Yes.
and it has like a refresh, relaunching the studio, can I just do that every time?
Oh, yes, yes. That's right. You can use one of your past sessions and just launch one again with the exact same options. Yes, you can do that. So
Okay,
yeah, that's a shortcut. Yep. I think I closed all my old ones, but if it was still up, you could see that. Okay. So now I'm in here. So what I'm going to do, you should be able to navigate in the Files tab through these directories to the worksheets that are already filled in. Okay. Because we're going to just run all the code up to the point where we left off last week, so that everything is as it should be in our environment, so we can continue. The data will be loaded, and all the models we fit previously will be in there. So I'm going to go to worksheets filled in, open the lesson 1 worksheet that's already filled in. Okay. Now I'm going to highlight everything. Let's see, everything up to, I believe we got up to this line 134. So you can highlight everything up to that point, and then either click Run button or hit Control Enter on your keyboard, and it will run. And I believe at least 1 or 2 of these models has to compile, so this might take a minute to run, but it should be relatively quick. Does anyone need help with that process?
I'm getting the CMD stand path has not been set yet error. What
Okay.
line of code is that again?
Or yes.
Clear it.
Let's see. Did anyone else get that error? So
I got it as well.
Are you in the Bayes 2025 project? You will need to go up here to the upper right and open that Bayes project. If it says project none, then are you in the Bayes project, Cameron?
Yeah, I thought it's saying it was, but I can open the project again.
Yeah, try to open it again, and maybe when it restarts that session, it will set the path. See if that works. Tell me how that goes.
The thing is, at the beginning on my console, it says CMD stand path set to, and then it has the thing. So I'm not sure why.
So it does say that. Well, here, yeah. Go ahead and well, yeah, tell me, once you open the project again, does it still have the error?
Let me run the code real quick.
Okay. Yes, that's right. Oh, yeah, that was what I was going to suggest next, Alina, was to just manually set the path if it doesn't, if it hasn't, yes, let me just go ahead and show that while we're waiting. So the code to set the path is, if you go back to the main Bayes 2025 folder, there is a, yes, Elisa, yes, that's what I would just go ahead and do. That's what we're doing right now. We're opening the worksheet filled file and running everything up to this line 134. Yes, so Cameron, if you still get the error, go into the main folder of the project, open this file called R profile, and then just click on source to run the entire run the whole thing. That is the code that configures all the paths.
Okay,
So if you
actually
still get
mine
the error,
works
just run
fine.
that. You got it going now?
Yep, it's good.
Okay, very good.
Thank you.
Okay, so let me go ahead back to the slides and we'll actually do some stats here. So we've added the fixed effect of nitrogen fertilization, right? We've added that, and that's how I'll just review our model code and formula up to this point. We have, if you remember, yield is our response variable. That's what we're trying to see, what factors influence yield, whether it's treatments or whether it's random factors like site and block that we're trying to account for. We have an overall intercept that's fixed effect. We have the fixed effect of nitrogen. So we're saying each nitrogen treatment level has a different mean that we're trying to estimate, and it's the same across all sites. It's fixed across sites. We have a random intercept for site. So we're saying each site may have a different yield. And we have a random intercept for block within site. So within each site, the blocks have variable yield. And this is the data that it comes from. And this tells how many Markov chains we're going to run and how many posterior samples we're going to take for each Markov chain. So 1,000 of them are warm-ups, and then there's a total of 2,000. So 1,000 after warm-up that we're actually going to use. That's what we've got so far. And then, yes, we checked the model convergence and everything, and we had got to the point where we said, okay, the priors on the fixed effect were completely flat, like I just said. We are not assuming anything a priori about whether a tiny effect close to zero or a huge effect are equally probable to us before we see the data. But that is not necessarily plausible because yield in our data set only ranges from like 0 to 40 or 50 or something like that. So obviously having a prior on the means that allow a prior on the fixed effect of nitrogen on yield that allows for effects in the hundreds, thousands, millions is not even plausible. So we can help our model to converge by setting a prior that will eliminate or assign a very low probability to incredibly implausible effect sizes. And that's just what we did at the end of last week. We said, okay, how about a normal distribution with a mean of 0 and a standard deviation of 10? It's sort of like agnostic to say the mean is 0. That means, right, half the bell curve is negative and half is positive. We're saying we don't even know if adding nitrogen is going to decrease yield or increase it. We think it's equally likely before we see the data. Maybe that's not even really that realistic, but it's sort of conservative. And standard deviation of 10 means eventually that bell curve, the probability drops off to almost zero. Once you get to like -30 or +30, it's pretty close to zero. And we think that's plausible because yield only varies by around 40 in our data set. So the means aren't going to be, and we still have a non-zero probability, even of very large effect sizes. We just are saying they're very improbable before we see the data. And we've added that prior by putting this extra line in that says prior, and we said prior normal mean zero standard deviation of 10, and class B. B refers to all fixed effects in the model other than the intercept. Everyone with me so far? This is review from last time. And we found that it didn't really affect our conclusions that much. It maybe made the third significant figure of the things go down a tiny bit. And then we looked at we'll look at this more later, so I won't review that now. Then we sort of manually went through how you would get the means for each nitrogen level longhand and calculate their different quantiles. And so we did that. I'm sort of going through this quickly because we did this last week. We did that this way in sort of a manual way by adding the intercept, the mean yield because the zero nitrogen treatment is our intercept level, and then our slope for 1 is the difference between 0 and 1. So if we add our zero mean to the difference between 0 and 1, we get our mean for level 1 of nitrogen. But we don't always have to do this in such a long-handed way because there's a package called EM_means that will automate that process for us. It will give us the marginal means, the posterior estimates of the means for each treatment without us having to go in and add and subtract intercepts and slopes and things like that. So I was just showing you that to show you how it works. And this is sort of the quicker way that I would do it in practice. And EM_means works for non-Bayesian models as well, but it has methods. So you may have seen it even if you don't do Bayesian stuff. If you're doing analyzing data in R, you may have seen this package before. But it has methods for BRMS models, which is very handy. So if we want the means for each level of nitrogen, we're going to use the EM_means function. Our first argument is the model fit, that object we created already. And the second argument is a one-sided formula. It does not have a y variable. It just has the fixed effects on the right side of the tilde. It says which factors in our model do we want to get the means for each level of? And our only one that we can do is nitrogen because that's the only one we have in the model so far. So we say EM_means of the fit, comma, tilde, n. So I'm going to run that code. Go on that line 139 there and hit Control Enter. And now if in your console you type n_EM_means and hit Enter, you can see what the contents of that object is. So here we see, here's the mean and the lower and upper 95% interval. By default, EM_means uses a slightly different kind of credible interval than we have been using, but it's going to come out very similar. So yeah, you see that the 0 one has a mean of 13 with a 95% interval between 10 and 16 versus the other ones are quite a bit higher than that. So this gives us some evidence for an effect of nitrogen on yield. And EM_means can also, if we want to know what is the uncertainty around the difference between each pair of means, we basically the way we do that is by subtracting the posterior samples for one mean from the other, and that's the posterior estimate of the difference between them. And it will also it will also have a credible interval. I'm sorry, is there a question?
No, I'm sorry, Reed. I was Quentin, I was in the breakout room and I accidentally hit
Oh,
leave
gotcha. No
instead of
worries.
share. Sorry.
No worries. But yeah, feel free to unmute and speak up if you do have a question. The function in EM means that does the pairwise differences or the contrasts is the contrast function, and we can do method equals pairwise, and that will give us all pairwise comparisons. So let's do that for the means. Oh yeah, you know what? I'm kind of cheating here because I'm using the filled in worksheet. I should go and use the one that has the blanks to fill in, and you all should too, so that you can you can see that I'm writing the code along with you. So the EM means was what we did last time, and this formula was tilde n. And next we're going to do contrast. Method equals pairwise. Okay, Control Enter. And here we have the differences between each pair of means. So 0 versus 1, it's sort of subtracting the lower one, the higher one from the lower one, so we get a negative estimate. Versus some of the other ones, like the difference between 1 and 2, the point estimate is closer to 0, and the upper and lower bounds of the credible interval are on either side of 0. So we sort of have the data are consistent with either a small negative or small positive difference. So we don't have much evidence for a difference between 1 and 2, whereas we do for, let's say, between 0 and 1 or between 0 and 2. There are lots of ways to plot posterior estimates that in R. I'm going to show you a few. There's two packages called tidy Bayes and ggdist that have, like, if you know R package ggplot2, there's a bunch of, they sort of are extensions or add-ons to ggplot2 that are specially made for plotting posterior estimates from Bayesian models. And gather EM means draws is a function that takes the output of EM means and puts it into a data frame that's easy to plot with. And then I've given you some different ways to plot it. So let's take a look at these, what these posterior estimates look like when we plot them. Gather underscore EM means underscore draws. I can hit tab to automatically complete that. If I run this line, it will take the EM means output and make it into a object that can be plotted. And now n underscore EM means is the name of the thing we're plotting. I won't explain the plotting code that much, but basically this is one way to plot the posterior distribution. I'll show you what it looks like. Let's see. Oops, I should have put post EMM draws in there. That's what we're plotting. So it didn't work because you can't just throw the EM means object into a plot. You have to use this object we've created that works with ggplot. You learn more from errors than from everything working well. Okay, so here's one way to plot it, right? So here are this is kind of a neat way to do it. Here you can see this dot is the median of the posterior distribution of the mean for each treatment. And I've got, since I put 0.8 and 0.95, I have error bars for different quantiles, the 80% and 95% credible interval. And this half I makes a sort of smooth histogram of the posterior distribution. So you can see the 0 nitrogen has a lower mean, and then it kind of goes up a lot between 0 and 1, and then a little more each between 1 and 2 and 2 and 3. But sometimes these bell curves can be kind of distracting, especially if you have a model that assumes normally distributed error. They always look like bell curves, so sometimes it's just a little much to include that. Like, I don't usually include these in a manuscript. This next one looks more like what you might put in a manuscript. If we want to do post EMM draws, and we're going to use the stat interval and to make the different credible intervals, and the stat summary to make the median point in the middle of the interval. So this is showing the exact same posterior estimates, but instead of the bell curve, it's summarizing it with different credible intervals, the 50, 80, and 95. And you could use other ones. If you there's no reason you have to be limited to these numbers. But I didn't specify any width, so by default, it's going to give you 50, 80, and 95, which is a good way to characterize a distribution. Any questions? So yeah, to me, this is kind of like what you'd want to present in a manuscript. And actually, in the further lessons 2 through 5, I really have a lot more specifics about how you might report a Bayesian analysis in a manuscript. So since I know that's what people might be interested in, so we'll talk a lot more about that as we go along. Okay, so far, we've only included the fixed effect of nitrogen, but the experiment was a multifactorial experiment looking at nitrogen, phosphorus, and potassium, N, P, and K. So we only just did nitrogen so far for simplicity, so you could see how fixed effects work and what kind of estimates you get. But really, we'd want to at least include main effects for N, P, and K in our model. We're not even doing interactions right now, even though in practice you'd probably include them. We will work our way up to that later. So basically, we're going to make another model, fixed NPK is what I call it, and it's exactly the same as our previous model, except instead of 1 plus n as a fixed effect, it has 1 plus n plus p plus k. We're adding in another set of fixed effects for each mean of the phosphorus treatment, each level of phosphorus, and each level of potassium. Other than that, and we're going to keep the same normal priors with mean of 0 and standard deviation of 10, because we've seen that they are good because they don't bias us to get any sort of effect. They just eliminate the probability of extremely large effect sizes that are literally impossible based on our data. So we're just going to put 1. By the way, if you omit the first 1, it will fit an intercept by default, but I'm just including the 1 to be explicit. 1 plus n plus p plus k. So yeah, you could delete this 1 plus and it would give you exactly the same model, because by default there's always a global intercept unless you specifically tell it not to by putting a 0 there. But it's a good idea to have a global intercept. And then we had site as our first random intercept, and block : site for block nested within site as our second random intercept. And other than that, I changed the random seed just because, but other than that, the code is all the same as before. So I haven't put any blanks there. So I'm going to hit Control Enter and run that. And because I have the pre-fitted model object saved in this directory, it did not have to compile and run. Okay, so let's see. We would like, before we go ahead and look at the model summary, let's look at the trace plots to see if the model converged, right? It's always a good idea to check model convergence, because if the model didn't converge, that means it's not the correct answer, and there's no point in looking at the parameter estimates. By the model, I just mean the algorithm that we're using, the Monte Carlo algorithm, to get the correct answer for this model. So we're going to go ahead and do that. So we're going to say plot fit underscore fixed NPK. I didn't put, for every model that we fit, I didn't always include in the code the trace plots and the predictive check plots, but it's good practice to look at them for every model that you fit. So I'm just going to type them in the console from now on. We'll use plot. You can see how does this look? Pretty good, right? We have good convergence. They're just going back and forth because that means they found the right answer and are going back and forth around it. And all the chains are right on top of each other for all our fixed effects. And you can hit enter to go through the plots. Here are some more fixed. So we have a lot more fixed effects now, right? Because we have one for every level of every treatment. Keep hitting enter. And then here are our random effect variance components. They all look good too. And we're going to use pp_check on the same model object, fixed npk, and that will show us if the model is a good fit to the data overall. And you can see it's getting there. We still are, it's a little, the data, the black line has sort of these two humps. Our model, the posterior distributions don't quite capture that perfectly, but the shape of the distribution is not skewed that much, so it's pretty decent. And now, if we look at model summary, we can look at the parameter estimates in a table. So here, I'll make this a little bigger. You can see now we still have our same random intercept for block and for site, but now we have a bunch more fixed effects, right? We have an effect for each level of nitrogen relative to the intercept, and also for each level of phosphorus relative to the intercept. There are our point estimates and potassium as well. You can see there's very high uncertainty around the phosphorus estimates. You know, even though the point estimate is 2, the 95% interval ranges from -9 to +14. So we don't really have, the data are equally consistent with a negative and a positive effect going in a pretty wide range. So that's not very strong evidence in favor of an effect there. And in a minute, I'll talk about some more ways we can quantify that. So far, so good. Are there any questions? So that model is pretty decent. We've added in all our main effects they want to add in, and we've also added in some random terms to account for the experimental design. However, we have assumed that all the predictors effects are the same at every site. We've only had a random intercept for site. That means, okay, the sites may have different baselines, but the effect of nitrogen at each site is assumed to be the same. We've just fit one intercept and one slope for each nitrogen level that are supposed to be valid across all the sites. But if you remember back to last week when we looked at the data, it actually looked like at some sites there was a strong effect of nitrogen fertilization. At others, there was no effect. The mean yield was about the same, regardless of how much nitrogen you added. So it's like, well, are we really modeling everything that's going on in the data if we are ignoring that and saying, okay, here's just one overall fixed effect of nitrogen across all sites? Well, how do we address that in our model? We can add a random slope term as well to allow both the intercept and the slope to vary by site. So not only can the sites have different baselines, they can also have different relative differences between the treatments at each site. How do we write that in our syntax? We add it to the left-hand side, the design side of our random effect. So right now, our site random effect term so far has always been one type site. So only one, meaning an intercept. We only have an intercept for each site. If we want a random intercept and a random slope with respect to nitrogen, so allow the nitrogen effect to vary by site, we would just add 1 plus n on the left-hand side. And you could do as many effects as you want on that left-hand side. We could do random effects for nitrogen, phosphorus, and potassium if we put that all on the left-hand side. Now, I'm only going to do this for site because we don't have enough data to do a random effect for a random slope for every block. Like there's only a couple of plots in each block. That's not really enough to look at whether the relative difference between the treatments are different in each block. But sites have replication so we can actually put random effects at least on the sites. We're not going to do it for blocks. That would be a little bit overfitting. So we're just going to do it for sites, if that makes sense. So we are going to do this. This next model is exactly like our previous. It has the same fixed effects. The only difference is this. in this, before it was just 1 by site. Now it's 1 plus n plus p plus k by site. That's the only difference. Other than that, I changed the random seed just for fun, but other than that, all the priors and model fitting options are the same. So let's go ahead and run that model. So 1 plus n plus p plus k is still our fixed effects, just like before. And 1 plus n plus p plus k by site, right? Because we're allowing the effects of our different treatments to be different at each site, because that's kind of what the data looks like you should do. And we're just going to do a random intercept for every block within site, because there's not enough replication within the blocks to even try to estimate a random slope at that very fine level. Other than that, the rest of it is the same as before. I've given it a new name, which is the name of the prefit model object that I've saved in the directory. So it will, when I run this, it will load that prefit object. Okay, I'm not going to show the trace plots and everything, the diagnostic plots. You can run those on your own if you want. I'll go ahead and show the model summary. And so you can see what kind of parameters we get now. Run that line summary. Here are the same, the fixed effects are the same ones as before, but look how many random effects we have now. Oh my gosh, there's so many, right? For block, we still just have the standard deviation of the intercept, but for site, we have a lot of parameters because we have each of those many levels, each has its own random slope by site, and there's also covariance between the intercepts and each pair of slopes. So you can see that it's a very complex model with a lot of parameters. Question if we can just, I would include 1 plus n plus p plus k by site for random slope. Yes, you in this random effect term, you should, if you want a random intercept, you should explicitly include the intercept, because there's also covariance between intercept and slope that is modeled. So we want to explicitly state that by putting that in there. You can fit the model without these covariances as well, but I like to include them at least for starters. Let's see, what did I want to say about that? So we can make, in a minute, we'll look at whether adding these extra complexity to the model made it a better model or not, whether it fits the data better. But before we do that, let's look at the predictions we can make. And so if we still wanted nitrogen predictions for this new complicated model, we're still going to get a mean prediction for 0, 1, 2, and 3 nitrogen, but now it's averaging over a lot of stuff. It's averaging over all those random effects of site and everything, and the block effects, and it's averaging over the different levels of phosphorus and potassium as well. So let's take a look at what we get now in this more complex model. What do we say about the difference between nitrogen levels? We'll use the EM means function. And run that. And now if I type n underscore EM means in my console and hit enter, you can see the estimated marginal means are somewhat similar to what they were before. However, the credible intervals are a lot wider because we have incorporated more different sources of variation. We were kind of not being honest with our previous model because we were excluding things that were part of the experimental design. Now that we've included the full design, the picture is a little muddier, right? Because the world is complicated and there's a lot of other factors going on at play besides just nitrogen. So we have more uncertainty. The difference is we have less evidence for a difference between nitrogen than we did, levels than we did before. And we can also see that if we do contrast of n underscore EM means, we're going to use that method pairwise, again, to get all pairwise comparisons. N_contrasts. If I type that in my console, you can see now there's a lot more, much wider credible interval on those differences as well. Many of them are going from a very negative to a very positive. So there's sort of equal evidence for negative and positive effects. So we can't really say one way or the other there. Sorry, back to the slides here. I wanted to show, I won't really go into the code that much, but I wanted to show you what does it look like when we can generate predictions for any combination of fixed and random effects using this function add epred draws, expectation of the posterior predictive. So we're saying what are the model predictions for any combination of fixed and random effects we want to include, and I make those predictions for every combination of nitrogen, and we're going to average over the block effects. We're just going to look at site effects, and we're going to say, okay, if at site 1, what is our prediction for each level of nitrogen, but always setting phosphorus at the control level of phosphorus and the control level of potassium, just to make it a little bit easier to look at. So we're going to look at every level of nitrogen predictions, but holding phosphorus and potassium at their control levels at every site. So we can make predictions conditioned on fixed effects, random effects, anything we want, and then I'm going to make a plot of that. What does our model predict? And so I didn't give you any fill in the blanks. You can just highlight that whole thing and run it to make the plot. So you can see that here are these black lines are the median predictions, and then we have credible intervals. So you can see that at some sites there's sort of no effect of fertilization, whereas at others there's this positive trend with low yield at the lower levels, and then it goes up by around 10 at the higher levels, although there's quite a bit of uncertainty in some cases. And I believe that you can see that the uncertainty is different magnitude for some of the different levels, and I believe that is because of the incomplete block design. Not all of the treatments are equally represented at each site. So some of the ones that treatment combinations with less data will have more uncertainty. But you can see this is actually getting us pretty close to what our data were saying originally, which was that at some sites there's no effect and at some there is. So we say, well, we sort of have this contingent effect where, due to differences between sites, the nitrogen fertilization effect differs from site to site. Any questions so far? So to wrap up lesson 1, I have a couple more concepts that we're going to be revisiting throughout all the other lessons. So we're gonna go through those, and you'll see these over and over again as we go. Yes. Oh, I forgot about this slide though. First, I just want to note, if you would go back to the raw data and look at the differences, the within site trends, the model, there are actually bigger differences than our model is predicting. So our model isn't fitting the data perfectly. It's assuming slightly smaller differences than we actually see in reality. And why is that? Well, that's what random effects do. It's called shrinkage. Random effects kind of, because of their a distribution centered around 0, the mixed model is pulling those estimates toward 0, making them less extreme. It's called shrinkage because they shrink towards 0. Why do we do that? Well, and that's not just a Bayesian thing. That is all mixed models with random effects will do that, whether it's classical statistics or Bayesian. The reason we do it is because we are scientists and we want to make general inferences about broader populations, about how things work in the world, not just about the conditions we did our little study in, we want to say, is that applicable to new situations? Like, should we make recommendations to growers about what to fertilize? Well, if we do shrinkage and don't fit our data set quite as closely and don't overfit, we actually make better predictions on new data and new situations that we haven't seen before. So it's just like a way to be a little bit conservative and not overfit the data you have to make better predictions in the real world, which I think we can all agree is good. So that's random effects are one way to do that, and priors is another way to do that. So if you have a Bayesian mixed model, you're doing it in multiple ways. Not fitting your own data as close so we can make better predictions in the real world. And yeah, I did later in other lessons, we'll look at interaction terms. You can add interaction terms to the fixed effects of the model by putting colons in between, like the interaction between nitrogen and phosphorus, for example, N:(P). There's also shorthand. If you write N*P*K, that will fit all subsets of interactions. It'll fit all the two-way, like N/P, N/K, and P/K, and N/P/K, the three-way interaction. But I left that as a homework problem because if you want to add interaction terms to the model, you can find it in the exercises. Okay. We talked about, okay, wow, we added all this extra complexity. We added all these random slopes, like fitting special site level variation in treatment effects and all of that. But was that all necessary? Did it actually make the model fit the data any better? Well, one way we can compare them, you may know about information criteria, AIC and that kind of thing. This is an approach that's equivalent to that. It's called leave one out cross-validation. Leave one out means, imagine we fit the model to all the data points except one and then predict that data point. So the model was fit not seeing that data point and then predict it. And we repeat that until the model is fit to all the data points. But we don't actually have to fit the model as many times as we have data points. There's actually a computational shortcut that you can use to get an approximation of that without having to refit the model over and over. And it is implemented in this function called add criterion that computes the leave one out, the LOO criterion for each model. So we're going to add criterion, and the second argument is the LOO criterion. That's what we're going to use. Add it to each model that we fit so far, and then we're going to rank the models with the function LOO compare. If you remember back, the models we fit, first we fit a model that had no fixed effects, only the random intercepts. Then we fit a model that just had the effect of nitrogen. Then we fit one that had nitrogen, phosphorus, and potassium fixed effects. Then we fit one with all those fixed effects, plus we allowed the effect to vary by site. We had random slopes for site. Let's see which one fits the data best. You can use k-fold cross-validation as well, but it actually does require you to refit the model many times, so it's a pretty slow process. But yes, you can use it. I think in a future lesson, I will show how to do that. Next week, we'll look at that. Great question. So we're going to use the function add_criterion for each of our models, and then and LOO is the criterion, and you can see we're assigning the result back to the original model, and that will save the information criterion analysis in the fitted model object to be used later. So I'm going to just run this whole block here. And I believe that since I ran this code already, the pre-fitted model objects already have it. Otherwise, it would take a minute or so to run that. And now if we use the LOO_compare and the arguments are a list of models, all of which have a criterion already computed for them, it will rank them and show which one fits the data best. I'll run that. Okay, and it will show the best fitting model at the top going down to the bottom. And this is ELPD diff, is the difference in the expected log pointwise posterior density. It's basically a difference in how well the model fits the data, and then there's a standard error of that difference. So the relative to the best fitting model, which has 0. And you can see the model with the random slopes is the best fitting model. So it was worth it to add that complexity. The model with only the nitrogen effect and with the other fixed effects are much worse fitting, and the standard error of the difference is much less than the actual difference. And the model with no fixed effects at all obviously is a very poor fit to the data because we didn't include any of the treatment effects in the model. So it was worth it because our data showed that there was a difference in treatment effects across sites. It makes sense that that it was worth it. It was worth it to add that additional complexity. So this is sort of accounting for the additional model complexity. It's still a better fit, even though it has more parameters. They were worth adding because they still let us make better predictions on data we haven't seen yet. So that's what this slide says. Now, the last part of lesson 1, we'll finish this in a couple minutes, then we'll take a quick break and start lesson 2. We have sort of been looking at the posterior estimates and being like sort of hand waving. Well, here's the mean for one treatment. It's over here. Here's the mean for another treatment. It's over here. Hey, they're kind of different. We have evidence for a difference. Now, in Bayesian world, that is really adequate evidence to say there's a difference. But many of you are probably familiar with p-values and null hypothesis significance testing. We want to test a specific hypothesis and accept or reject it based on the evidence from the data. Well, we can do that in Bayesian world as well in a slightly different way. The sort of more classic way to do it is called Bayes factor. This is not used as much nowadays, but I'll explain it to you in case you see it in the literature. I don't really recommend that scientists use this way, but I'll show you some other ways as well. Now, the Bayes factor is basically the ratio of evidence between two models. If you remember back to last week, the posterior is the probability of the model given the data, how likely our parameter estimates are to be true given the data we just observed. If we take the ratio of those two probabilities, we can say which one of our models is more probable, more likely to be true. And obviously this ratio could range from, it could go almost all the way down to 0. It could go, there's no upper or lower bound to this. But and that ratio is called the Bayes factor. Now, if it's equal to 1, that means we have equal evidence for the two models. There's one of them is as equally likely to be true as the other. And if it's greater than 1, then the one on the numerator, the model 1, is more evidence. Now, there's no universally agreed upon significance threshold, like the common p equals 0.05 cutoff doesn't really exist, but many authors have sort of thrown out the number 10. If one model is 10 times more likely than the other to be true, that's significant, right? But it's like, just like 0.05 is kind of arbitrary. The Bayes factor threshold is also arbitrary. It depends on your needs. Like maybe you want 100, or maybe only 5 is good enough for you. Well, they've thrown out the number 10, but take that with a grain of salt. We can calculate Bayes factors for any parameter or estimated marginal mean or anything we want in a model. And so, right, in the previous slide, I said, well, there's two models competing. What are the two models we're comparing? One is our posterior and the other is our prior, the model that we assumed before seeing the data. And if you remember, we used priors that were normal distributions centered at 0. You could think of that almost like a null hypothesis. We said, we're assuming that there's equally likely to be a negative and a positive effect. The mean is centered at 0. We've got sort of null priors. So you could think of this Bayes factor almost like a null hypothesis test, because our priors are like a null hypothesis. They don't have to be. You could have a prior that's not a null hypothesis, but in this case they were. So what does, and so our numerator is the posterior, our parameter estimates that we got after we saw the data. Our denominator is our priors. What is the ratio of the probability of those? If it's 1, if Bayes factor is 1, that means we did not change our belief about the parameters distribution at all after seeing the data. Our prior has survived and it's stayed the same as it was before. If our Bayes factor is greater than 1, we have more evidence for the posterior than we do for the prior. That means we've changed our beliefs about the parameters after we've seen the data. You can also get a Bayes factor of less than 1. That means we actually believe in our prior even more. We have even stronger evidence that the prior is true after we've seen the data. So sort of more significant, more evidence for an effect would be a greater number, above 1 and on up. Make sense to everyone? So we can, basically the way we would get Bayes factors here is, let's say we care about our contrasts, our difference between yield means for each pair of nitrogen treatments. The way we would get that with the Bayes test R package is we would have to use, we've sampled from our posterior distribution, but we have not sampled from our prior distribution. We didn't bother to. So we're going to go back and use a function called unupdate, which will get samples from the prior distribution, as many as we do for the posterior. And then we will calculate the same estimated marginal means and contrast. So we have posterior distributions for the differences between our means of the nitrogen treatments. We're going to go ahead and compute prior distributions for those means. And then we're going to use Bayes factor to compare them to the ones we got before. So if that doesn't make sense, if you remember, so here, if you type n_em means into the console, so here are our posterior distributions for the differences. I'm sorry, n_contrast is the one we want. Here's our posterior distributions of the differences, right? Between each pair of treatments. Let's get the prior distributions for those differences. We're going to use our unupdate. And that will get our prior distribution of the parameters of the model. So it says sampling priors, because that's what it's doing. And then while that's running, we're going to use the em means function. And you can see that I'm using this prior distribution of the prior from the model and to do the em means and do the contrasts. So I'll run these two lines of code here to get those. Okay, and then you can see in the slide, Bayes factor underscore parameters will calculate a Bayes factor for each of those contrasts. And we have to say, what is the posterior? It's the contrast we observed. And the prior is that prior contrast. Oh yeah, you can look at here, what does n contrast prior actually look like? We'll put it in our console and take a look. You can see that the estimates are all right around 0, right? They're centered, they're almost exactly 0 with a credible interval going from -20 to +20, right? Because it's a null hypothesis. So you can see how the priors represent a null because they're all centered at 0 and are sort of equally likely to be negative as positive. Like we think it's equally likely a priori that this treatment will be higher versus this one. Let's see how our beliefs changed after we saw the data. Bayes factor underscore parameters. The posterior distribution is the contrasts, and the prior distribution n contrasts underscore prior. Okay, and then I'm going to run that and we'll see the Bayes factors. Okay, so you can see that the Bayes factor is pretty close to 0 for many of these, except for the difference between 0 and 2. The Bayes factor is about 7. If you remember, 10 was the number that was thrown out there as the as kind of the significance threshold. So that's the only one that's close to it. Other than that, we are still believe that it's roughly equally likely to be true that there's no difference between the treatments as there is the difference we observed. So yeah, you can see the difference between 0 and 2 was about 4 units in our posterior estimate. So that's the one that was the largest magnitude, more or less. So it has the most evidence for it. The rest are kind of close to 1, if not a bit less, or they are less than 1. Now, there is an issue with the Bayes factor, right? Because Bayes factor is the ratio of evidence of the posterior to the prior. That means if we chose a different we could kind of almost manipulate the Bayes factor by choosing different priors. And so they're very sensitive to your choice of prior. So many people dissuade the use of Bayes factors because we don't want, even though our parameter estimates were not that sensitive to our choice of prior because our model had enough data to not be that sensitive to the prior, the Bayes factor is. And it also requires a lot of samples from the posterior to be precise. You saw a warning when it popped up that we need a lot more samples to get a good estimate of the Bayes factor. So those are sort of some strikes against the Bayes factor. Well, what are some other alternatives we could use? There are a couple of Bayesian analogs to p-values. The other thing about the Bayes factor is it doesn't look like a p-value. It doesn't, p-values are more significant when they're very small numbers close to 0, but Bayes factors are not. So it's sort of more familiar to people in the literature if you use a value that follows the same scale as a p-value. So there's one called probability of direction, PD. That is the proportion of the posterior distribution that is on the same side of the null as our point estimate. So you can get this. That's sort of the probability after we've seen the data that our effect size is positive, for example. And that will, the closer that is to 100% probability, the more significant, but you can actually use the argument as underscore p equals true to get it in the form of a two-sided p-value. And we have to specify we can use the function PD to get this, and we have to specify our null is 0. So, because sometimes if your parameter is a ratio, an odds ratio, for example, the null hypothesis would be that the ratio is 1. So we're specifying the null is 0 because we're looking at the difference of two means. So we can use the PD, probability of direction, null equals 0. So you can see that the probability of direction for this one is close to 100%, indicating evidence in favor of that difference being greater than the null value of 0. Yeah, as I said, if you add the argument, I didn't put this in the worksheet, but if you add as underscore p equals true, it will give you it in the form of a two-tailed p-value, very similar to what you get from classical statistics, frequentist analysis. So here's that value, which if you want to say 0.05 is a significance threshold, it's below that. So that's the one we have the most evidence for a difference. Now, there's a lot of different ways to calculate a p-value like number from a Bayesian model. Another one is called PMAP, maximum a posteriori p-value. I won't get into the details of this. It basically is, it'll take your posterior distribution and then say what is the density of that posterior at the null value versus the mode, the difference we observed. And that ratio, the closer it gets to 0, the more evidence. So p point null is the function that is used to get that one. And we specify null equals 0. So that's just another way to do it. You can find references in the literature justifying either one of these p-value analogs. They usually give similar answers. Sometimes it varies a bit. You can see we get again, this one is 0.02. whereas the other ones are quite high. So that's the only treatment difference we have evidence that is different than zero of any appreciable evidence. And yeah, just to note that these values do not require you to use the prior distribution in any way. So they're not as sensitive to the choice of the prior. However, they are sensitive to the internal workings of how we're estimating the posterior density. So with any of these things, the more posterior samples you take, the better, because you're going to get a closer approximation of that distribution. We're only doing a few thousand in this lesson just to be quicker, but you could do a lot more than that in reality. Any questions? Yeah, so can you do ANOVA on a Bayesian model? Technically, yes, but it's not really something that is done in a Bayesian framework because ANOVA is doing like F tests in null hypothesis testing to look at whether the variance ratios are significantly different from zero. But in the Bayesian framework, you're not really assuming that anything is exactly zero and trying to test against that. You're trying to estimate the effect size and the uncertainty around it, rather than trying to test whether it is exactly zero or not. I mean, I did show you how you could kind of do that in a Bayesian framework, but yeah, there's no real Bayesian ANOVA necessarily. So you wouldn't really do an overall F test or something like it for treatment. I mean, you could do it, but it's not really done. You don't see it in the literature. So yeah, not commonly. But thanks for the question. Yeah, so that is all for the first. Well, we're kind of knocked out last week's stuff. Yeah, so Cameron got slightly different values. Yes, if your random seed is a little bit different, you will get a slight right. So right, the interesting thing about the Bayesian algorithms, the algorithms we're using to fit Bayesian models is there's nothing random about the Bayesian model per se, right? It's a formula with equations where you have to integrate a distribution and get an answer. The reason that the values vary a bit from time to time is because we cannot get an exact value for that integral. We have to use computational and numerical methods to approximate the integral, and those computational methods involve random sampling. They're Monte Carlo. So because we only took a finite number of samples, there's a bit of sampling error, and you will get slightly different results each time you do it. If we would sit here and run the thing for hours and get hundreds of thousands or millions of samples, we could get them exact down to many significant figures if we wanted to. But those are, you know, only those are not really significant in reality, right? Like they're, you often see, this is one of my pet peeves in the literature. People will say, okay, the mean yield in the control group was 5.7639, with a standard error of 2.53. It's like, well, if the standard error is, 2, why are you reporting the mean to 5 significant figures, right? Because you might as well say 5 because there's actually not that many significant figures that you should report. But yeah, for some reason, people that write science papers thinks it seems more scientific the more decimal points you put after something. So yeah, it's a pet peeve of mine. But yes, because the Bayes algorithm is random, you'll get a little bit of variation each time. Yes. So yeah, I think this is a great time to take a break. So why don't it's 3:11 on my clock. Let's break. So that's 2:11 Eastern. Let's break until 20 after, until 3:20 or 2:20, and then we'll resume. Yes, I will. I'm going to go to the restroom real quick, but I will be right back to answer questions anyone has during the break.
Let me try to get these things. Oh, please.
Hey, Adam. Well, you got here at a perfect time. We're taking a break. We finished lesson one, and now we're going to start lesson two in just a couple minutes. So yeah, you came at a perfect time. You didn't miss too much, hopefully. Plus, you don't have to say sorry for coming and going or showing up or not showing up. There's no grades or anything like that. So it's just it's all voluntary. So no worries either way. There's no exam at the end of this. Oh, by the way, has the connection been good? Has everyone been able to hear me the whole time? I know last week we had some issues with that at one point. But anyway, please let me know if anything is not coming in. Okay, great. Glad to hear it. So we'll start again in just a minute. Oh, I meant to ask this at the beginning of today, but I forgot. But now is a good time because it's in between the lessons. I don't mean to put people on the spot, but can anyone tell me the most interesting or most useful thing they've learned so far from this? I'm curious what anyone has to say on that. You can put it in the chat or say out loud or whatever. Or just say one thing you've learned. Okay, yep, people say it's more flexible, that a way how to compare models. Yes, definitely those are cool things, right? Yes. Very very timely, Elizabeth, to talk about priors because our first part of lesson two is a bit more in-depth exploration of priors. So yes, glad you said that. And yeah, the Bayesian approach makes more sense. Yeah, I mean, I'm inclined to agree, although again, it's all tools in the toolkit, but I am inclined to agree. And it just works better too in a lot of ways. Cool. Well, thanks. Thanks for you know, making me happy by saying all that stuff. So let's go ahead and get started again. I will screen share here. Oh, wait a minute. I'll do it this way. Hold on a second. There we go. So we are going to go ahead and start lesson two. Now, lesson one was by far the longest one. So hopefully we'll do most or all of lesson two today. And, we'll just do whatever we have time for. We have time in this series to cover all the material. So let's just real quick review what we've already learned, in case you forgot already what you learned. Again, we're going through this whole course to learn how to fit Bayesian, multi-level, or mixed models. And yet we already know how to follow along with the slides. What have we learned so far? Well, sort of the broad concepts where we learned the basics of Bayesian inference. We learned what priors, likelihood, and posterior are, and how to estimate uncertainty in parameter estimates using credible intervals. And we learned a bunch of different techniques. Specific tools in our toolkit now include using this special kind of Monte Carlo sampling to fit Bayesian models, because as we know, they're very hard to estimate those high dimensional integrals without some special tricks like Monte Carlo. We've done a mixed model with random intercepts and random slopes. We've done a little bit with priors. We're going to do more. We've looked at model convergence. So like, did our algorithm give us the correct answer to that integral so that we can trust the results we get from the model? We've made plots. We've looked at model predictions. We've compared models, and we've tested hypotheses using these sort of Bayesian style p-values. If hypothesis testing is what you need, we can do that within the Bayesian framework. What are we going to learn today? Well, we're going to go, we didn't really look, we sort of looked only very shallow level at priors. Now we're going to look more specifically at how we can vary priors and how that might influence our results. And then in terms of new models we're going to learn today, so far the model we fit was a mixed model where we assumed normally distributed error. We're going to do generalized linear models now where the error in our is not normally distributed. And we can do GLMs, and we're even going to do GLMMs, generalized linear mixed models, because sometimes you have both non-normal data and you have a mix of fixed and random effects, so you need a GLMM. And as we go, especially, I didn't do this as much in lesson 1, but for all the lessons following, I'm going to try to explain it as if you would be doing this, analyzing data that you actually want to present in a publication or presentation. So try to go through the whole data to doc pipeline, right? Start with the raw data, look at it, fit model to it, make model predictions, put those model predictions into graphs and tables and textual descriptions that you would report in a manuscript. And so there are different packages that are needed on each step of the way there, especially we've used EM-means and Bayes test R already. We're going to use tidy Bayes and ggdist to make the plots, and GT is a very nice table creating package in R that can make tables of the parameters and predictions and things. Okay, this is a good time to step back and review Bayes' theorem, since this is the fundamental equation that pretty much everything we're doing is based off of, even if it's kind of behind the scenes and you don't really see it when you're just doing R code and stand code. This is what everything is based on, right? The probability that A is true given that B is true is equal to the probability that B is true given that A is true times the ratio of the probabilities that A and B are true. Again, that's a lot of mumbo jumbo in a way, but we use it in the world of statistics, where A is our model parameters that we've estimated and B is our data. We want to know if we see this data, and then how likely is it that the statistical model we've fit to the data is true, right? And so probability of model given the data, that's our posterior, and it is proportional to the likelihood times the prior. Probability of the data given the model, that's the likelihood, and the probability of the model, so the probability of our parameter estimates before we've seen the data, that's our prior, right? The prior is just P model. Data is not included in it, so the prior is what we know before we see the data. All the other terms have data in them somewhere, so we need data to get them. And this P data is just kind of a normalizing constant, because prior probability distributions always have to integrate to 1 because they have to accommodate, 100% of all possible outcomes. So this thing is just in there to make sure that to normalize, so the integral is 1, but it's the most annoying one, and it's that big integral that we have to spend all our time sampling with Monte Carlo. But the posterior, what we know after we fit the model to data is equal to the prior, what we knew before, times the likelihood, the new information we got from the data. Start with what we believed before, get some new information, update it to what we know now after we got the data. It's just intuitive. There's a lot of math behind it, but I think the basic intuition makes a lot of sense. And yes, that is what this slide says, right? The prior is, and all of that is not just hand waving, right? There's actual numbers that go with all of that. The prior is a formal statistical distribution with parameters, numbers of what we think the parameters like the intercept, slope, all that kind of stuff are without collecting any data yet. Probability of the model not dependent on the data. After we get some data, we calculate probability of data given the model. That is the likelihood. It just depends on the data. How likely was it to observe? Because it's across all possible combinations of parameters we could have in our model. So the full distribution of how likely it was to observe the data that we did given any possible parameters we could have in our model. Like if we observe, like going back to coin flips, if we observed, 5 out of 10 heads, we would say, okay, all possible combination of parameters, right? Like you could either have the probability of heads be 1 out of 10, how likely was it to observe 5 out of 10? If the true probability was 2 out of 10, how likely was it to get 5 out of 10? 3, 4, 5. We've got a full likelihood distribution for every possibility of parameters that we could have in our model. So the likelihood just depends on the data. It covers all the possibilities of model parameters that we could have. And then again, we divide by the marginal probability just to normalize and make it equal to, make the integral have an area of 1. Multiply it all together, you get the posterior, our new knowledge of the world after we collected the data. Again, it's a formal statistical distribution of what we think those parameter estimates are, how probable they are to be true. Any questions or comments so far? So yes, the posterior, it's a product of the prior and the likelihood. I try not to overdo it with like the memes, but every now and then you have to throw one in, right? It's the posterior is a combination of what we knew before we got the data, updated with new information that we got, right? And so just like we were talking about with Bayes factors, if the new information changes our beliefs a lot, the posterior will be very different looking than the prior, and it's more surprising to us, right? Like if the new information just confirms what we already knew, that shouldn't change our prior that much, and we'll keep it about the same. So the Bayes factor, or whatever you want to use, is kind of like a measure of how surprising our data were given the prior. Similar to a p-value in that sense. So yes, if you use any classical statistical method, you're using likelihood. You don't always say it, but any ANOVA, t-test, all of that is likelihood based. Classical statistics and Bayesian is always using likelihood, right? Because the likelihood only depends on the data. So since frequentist classical statistics do not allow you to formally incorporate prior knowledge and only let you use the data that's in front of you, their entire inference is based on the likelihood. That's it, just likelihood, just the data. So there's nothing Bayesian about likelihood. Everybody uses likelihood. Bayesian uses priors, right? That's the difference. Now, priors scare some people, that they have a bad reputation. It is kind of one of the reasons why Bayesian statistics were seen in an unfavorable liked by many statisticians for many years, because people say, well, priors are subjective. They don't depend on the data. We as analysts set the priors. So why can't we just set them to get the result that we want, right? Like, it's subjective. That's actually a decent argument. I mean, it's understandable that some people feel that way. Well, how would we as Bayesians respond to that argument? Well, number one, right. Yes, priors are a subjective assumption, but all statistical analysis involves assumptions, even if it's just based on likelihood. Let's say you're fitting a linear model, not Bayesian, whatever, any kind of linear model. You are making a lot of assumptions. You're assuming the relationship between X and Y is linear, that if X increases by a certain number of units, that Y increases by a proportional number of units, right? So that's a pretty strong assumption. Not all relationships in nature are like that. And we're also assuming the error around that trend is normally distributed. Also quite a strong assumption. It's only a rough approximation of the real world, right? The normal distribution is a mathematical function. It only exists on paper. It does not exist in reality. Yes, it's a good approximation for many processes that occur in the real world, but it's still an assumption. It's still an approximation. It's not always true. So if you were saying, I'm never going to make any assumptions, you're never going to be able to fit any model at all, because a model is by definition a simplification of the real world that makes assumptions. Another argument, yes, I see that Elisa made a comment that Bayesian approach using priors actually is a better way of corresponding to how people actually think in reality, and how animals and other non-human thinkers make decisions as well, which I think is completely true. But that might sort of like a better way, if frequentists are making these arguments on the grounds that priors are subjective, I think it's best to respond to it with quantitative rebuttals. So that's why I focus on these rebuttals, even though I completely agree. So the another argument in favor of priors is kind of like, well, we're really using them more for practical computational reasons most of the time than we are because we truly have some strong subjective belief. Like, if you have a lot of data, actually the prior distribution doesn't even influence your results that much. The likelihood is really having most of the influence on our posterior. The prior is just something that we use in many cases to make the computations needed to fit the statistical model a little bit easier, to help us converge on the right answer. And in many cases, a likelihood-only approach will not be able, it will fail, and it will not be able to get an answer. We actually need that little bit of extra help from the priors to constrain our answers to a reasonable range to even get an answer in the first place. It's just a more pragmatic argument. And another argument I would say is, okay, yes, they're sensitive to assumptions, but we should always check the sensitivity in any analysis we do of the assumptions we make. If you think that assumption is major, prior, whether it's a prior or whether it's something else, you should check whether the results are sensitive to it and report that in your manuscript or whatever, right? Like, if you tried different priors and the results were about the same every time, you should say that in your manuscript, because that's a good thing, right? And if they do change, if they are sensitive to the prior, let's present that in our manuscript as well and allow the reader to decide. But what would be a little bit dishonest is to knowingly present results with one prior as if it was the only possible answer, even though you know that varying the prior will change the results qualitatively. That would be obviously not legit. So yes, definitely be above board when you do any kind of analysis like this. Let's go through a little example. First, we'll do one. I'll just talk you through one, then we'll do one in code as well. Okay, let's say we have trying to develop a vaccine. We're immunologists, and we have come up with a new vaccine. and see how it can boost immunity to a disease. Just for simplicity, we're going to say the baseline immunity rate in the population unvaccinated is 50%. Okay, we're going to make a kind of pessimistic or conservative prior assumption that the vaccine might be effective and it might be ineffective. So we're going to set a prior with the most probable. We're going to say the most likely outcome is that this vaccine is ineffective, that it does not increase the baseline immunity rate at all. In fact, it might even decrease it. And so we're going to make our prior centered around this 50% baseline. But obviously, it's a distribution that goes above and below that. That's a very conservative prior. Okay, that's our prior. Let's get some data. Here's three, so let's do three scenarios. Let's say we have a small budget and we're doing a small sample size. We only can test 10 animals. For this simple example, we're not going to have a control group. We just vaccinate 10 animals because we already know, for whatever reason, the baseline rate is in the control group is 50%. Let's say we only did 10 and we saw 7 developed immunity and 3 did not. So obviously we observed 70%. In our second scenario, let's say we got more data, tested 50 animals with the same ratio, 70% were immune. Or what if we did 100 and saw 70 to 30? What will our posterior be with these variable amounts of data that we got? Well, the more data you have, the more influence the likelihood has compared to the prior. And so the closer the posterior will get to the likelihood. So here's our first scenario with the small sample size. Here's the orange line is the prior. You see it's right around 50%. The likelihood is our observations. It only depends on the data. You see that it has its peak at 70%. That was what we observed. The posterior is basically multiplying these two curves together to get this green curve. You can see that it is not, the mean of it is not 70%, right? It's in between 50 and 70% because we've gotten only a little bit of data from 10 trials, 10 animals that we're saying, okay, now the most likely thing is that the vaccine gives you about 60% immunity because we only got a little bit of evidence. So we're still sticking with our original wishy-washy belief that it might help and it might harm, but we now think a little bit more that it's helping. If we did 50 animals, look, our likelihood is still centered at, the prior is the same, but our likelihood is still centered at 70%, but it's skinnier, right? There's more data, so we have a tighter likelihood because we got more data. Now look, the posterior is being pulled more toward the likelihood. It is, getting close to 70.7 as the mode of that distribution. If we had 100, we're even closer, right? Like the posterior, it's not quite there with 100, but it's darn close, right? It's almost exactly lined up with that likelihood. Now, the more data we would get, if we kept going and kept observing like 700 to 300, eventually the influence of the prior would completely go away and the posterior would look exactly like the likelihood. So the more data you get, the less influential your prior beliefs are, and the more influential the data are, which makes sense. The more data we see, the more we can trust it, basically, and the less we are tied to our prior information that we had before we collected the data. Any questions on that? So yeah, so that's what I just said. Now, clearly, you can see that the more data you have, the less influential the prior is, so the less sensitive your results will be. But what if we have a very small data set? We're going to do a hands-on example, and intentionally picked a topic that, at least in the past, was seen as controversial to the point where prior beliefs may differ in among scientists of whether this is sort of what the effect is likely to be. And so, right, so in the example we did so far, right, we have 3 different likelihoods, 3 different size data sets, but the prior is the same every time. This time, we're going to use the same data, different priors. The same likelihood every time with different priors, and see what effect the prior has. Right, so let's go ahead and go back into our RStudio server session and get set up for lesson 2. So what I would recommend is you can save your worksheet. You can close all the lesson 1 worksheets. And then I'm going to go ahead and just restart the R session. And I have it set to delete all the variables in my environment whenever I restart the session. But if you like, you can, if you don't have it set that way, you can click on this broom icon here, which will delete all the will clear the environment as well. So you could do that as well. I'm going to go into the Files tab here. I'm in the Bayes 2025 directory. I'm going to go into Worksheets. I'm going to open Lesson 2 worksheet. And then I'm going to go ahead and run the first chunk of code to load all the packages, set plotting options. Oh, and I've set this colorblind friendly color scheme there, which I'll use for all the plots. And then, well, that will create the model fit directory if it doesn't exist yet, but it already does exist. Okay. And then because I'm running this on Scinet, I will run line 31 to set the BRMS options to use the Scinet to CMD stand backend. But if you're running this on your own machine without command stand, you would run that line instead. Hopefully Grant can help you if you need help with that, getting set up. Okay, so we did that. What we're going to talk about is GMOs and whether GMOs, transgenic maize that has BT, so it is been genetically modified to be toxic to pest insects, whether that has non-target effects on other arthropods living in the community, which is one of the arguments that was sort of made against GMOs. But then defenders of GMOs would respond and say, well, actually, these GMO, since we don't have to spray with pesticide as much, it actually has less negative effects on arthropods living around it than conventional corn. So this is just a very, very simple example data set. It's in the AgriDat package, like many of the example data sets we're using in this workshop. Basically, it's just a very small data set that was published by Gottman et al. So it's called Gottman BT. And it is the abundance of some, I don't even know what, arthropod taxon. And some of the measurements were taken on transgenic maize and some in the control group, not transgenic, isogenic line. And we want to know, okay, is maybe the BT corn has bigger impacts on non-target species than conventional with insecticide, or is it safer? So we're going to load the data, and then we're going to plot it. Isonoptera is the taxonomic group that they looked at the abundance of, and so we're going to make a box plot for each for the control group and the transgenic. And this is only a very small sample size. There's only n equals 8 observations in each group. So we want our x-axis to be well. First, we're gonna load this data, and then if you type the name of it in your console, it will show the data. You can see there's only 8 observations from each group. There's another response variable. We're just going to look at this first column or second column, Thysan, right here. And so the X variable is gen, GEN for genotype. That's the name of the column in the data set. And the Y is going to be this Thysan column. And then we're going to use the geom underscore box plot function to make a box plot of each group. Hit Control Enter. You can see that well, the median abundance of these bugs is higher in the BT than in the control group. So it's like, well, we can see from this very small data set, just looking at the data, it looks like BT is not having negative effects on these arthropods. In fact, it's having more positive effects compared to conventional insecticide management of maize. But again, this is only a very, very small data set. Is 8 observations enough to say that's the reality and that's what it is? Like, what about all the literature and prior information we know about this stuff, right? That's what we're going to look at. And I just wanted to do a step here so that we're going to set the factor level ordering so that the control line, which is called ISO for isogenic, is treated as the reference level in the model, so that if we get a positive slope, a positive coefficient in the model, that means BT is better or has higher abundance, and negative would mean control is better. We're going to use the mutate function, which changes the value of a column, and we're going to use relevel ref equals ISO. So re-change the levels of the order, the factor level ordering, so that ISO is the reference for intercept level. Level ref equals ISO. Control Enter. So that's just setting that. Okay, let's say we're not Bayesian. We're just going to do a simple t-test, right? We're comparing the mean of one group to the mean of another. For that, in classical frequentist analysis, we would just use a t-test. It only uses the likelihood. It just comes from the right t-test is only looking at the data, just the likelihood. It's frequentist, so we're saying, is there enough evidence to reject the null hypothesis that the two means are equal? The mean of the BT and ISO are equal. No prior knowledge is incorporated in any way formally. T.test is the function in base R for a t-test, and we formula equals Thysan by gen. So is the Thysan mean different by genotype? T.test. Thysan by tilde genotype. So we see, yes, indeed. Yes, indeed. We see that there is a negative, a p-value close to 0 or less than 0.05. So we have strong evidence from this data set that the alternative hypothesis is more likely than the null hypothesis. The true difference in means is not equal to 0. Pretty basic stuff. Now, let's do this in Bayesian world. If you look at the data, you can see that the means are, the lowest abundance was 4. I don't know what units these are in, but it goes from about 4 to 18. So we could say, okay, then we'll say in that if those are roughly the order of magnitude that we have, then an effect of plus or negative 5 in either direction would be a big effect. So I'm going to fit this model 7 times with 7 different priors. First, we're going to use the default, a completely uninformative flat prior, right? That's the default of BRMS. It assigns equal prior probability to any effect size. Again, as we've talked about before, that's not necessarily realistic because it doesn't even tell us the order of magnitude. We usually at least have an idea of the order of magnitude, even if we don't know which treatment will have a higher mean, whether it'll be positive or negative, we can at least get it within an order of magnitude or two. So a completely flat prior may not be reasonable. Okay, but what are some other priors we could use? These are all going to be normal distribution priors. We could have a normal centered at 0 with a standard deviation of 5. And what would that mean? That would be like we don't know if the effect of BT is positive or negative. It's 50% likely to be positive, 50% to be negative, but we think that the possible range of effect sizes are likely to be pretty big. There's a moderate probability of a large effect, whether positive or negative. We could also use normal with a mean of 0 and a standard deviation of only 1. That means we actually think that BT and ISO are not going to be very different. We don't know which one will be higher, but we kind of think that the difference is going to be pretty small, right? We're saying that there's not a high probability of a large positive or negative effect. But you don't have to use 0 as the mean of that normal. You could use 5. You could say normal with a mean of 5, standard deviation of 5. We think that BT is going to have a higher abundance, but we don't really know, so we're putting a high standard deviation. If you did 5 and 1, you say, well, we think it's going to have a higher abundance, and we're very certain. We think that the likely effects are going to be right around 5. And of course, you could do the opposite with negative 5 as the mean. So those are 6 possibilities, right? We're going to do the default and then all 6 of these possibilities. We're going to fit the model 7 times. So here's our flat prior. We're going to use BRM to fit the model. And every time the formula is going to be thisan by genotype, just like we did in the t-test. And the data is going to come from gathman.bt. That's the name of the data frame with the data in it. I'll hit Control Enter to run that flat prior model. And then we're going to use the first prior that says, okay, we think that there's probably, we don't know which one's higher or lower. And we kind of think that it'll be within this kind of 5 range. So we're going to use 5 as the standard deviation. Prior equals prior parentheses normal parentheses 0, 5 parentheses comma class equals B. B being the terminology that is used for fixed effects. This model only has one parameter in it, basically the fixed effect difference between the two. Oh, and remember, if you don't want to type all this in or get stuck, you can always go to the worksheets that are already filled in, and you can find all of this already typed in. Again, I recommend typing it in. And then we'll do normal 0, 1. That's the third model. It's very tight regularization, right? We're saying large effects are not very likely. Now we say, okay, BT is likely to have a positive impact, but we're not sure how big that impact will be. We'll make the mean of 5, standard deviation of 5. We already went through the other possibilities. Mean of 5, standard deviation of 1. We could also do mean of negative 5, standard deviation of 5. And lastly, mean of negative 5, standard deviation of 1. And that covers a lot of possibilities. So then let's go ahead and run models 2 through 7 with the 6 different normal priors, all of which have different means and standard deviations. Okay. Now, here is some code to pull out the median, lower, and upper confidence interval limits of the difference, posterior estimate of the difference from those models, and then put it together in a data frame for plotting. So I'll just run that code. Don't worry too much about exactly how the code works, but basically each model has taken the prior and the data and got us a posterior distribution of what we think of what the model's estimate of the difference between those treatment and control is. I'm going to highlight that. I'm going to run that code. Going back to the slides. Okay, we've run that. Oh, by the way, yes, I should have looked at the slide first, but I just want to point out I did not include anything about how many Markov chains, how many iterations, and so forth, because the default is 4 chains, 1,000 warm-up and 2,000 total, which is more than enough for this very simple model that has basically a intercept and one effect of a difference between 2 groups. It only has 2 parameters, so that's more than enough. You don't really need to mess with the defaults there. And if you look, the only blanks I've left you is the x-axis on our plot we're going to make is the prior, which of the priors we're using. Y is the median, the median of the posterior estimate. And then the minimum and maximum of the error bars. Y min is lower 95, the lower bound of the 95% credible interval. Y max is the upper bound of the 95% credible interval. So X is the prior, which prior was we assumed. Y is median. Y min, lower 95. And Y max, upper 95. And then, yes, I believe we're going to do a geom_point range, which will give us a point with an error bar on it. Let's see what we get. Okay, so here's an interesting plot. You can see the flat prior will give us an estimate just like the t-test, right? It is not assuming any prior, so this is going to come out as just what the data said, basically, which is that BT has a higher abundance of the arthropod. And if we have a normal prior with a wide standard deviation, we get a very similar inference to what we get if we have a completely flat prior, because this prior is very, very wide, and it's not biased in one direction or the other. Now, what if we had our normal with a prior with a mean of 0 and a standard deviation of only 1? Well, look what we get there. We get something very different than what the t-test gave us. We get a almost 0 with a credible interval that actually well overlaps 0 for the estimate, because we had a very strong prior that had a very tight standard deviation. We said, we really don't think that BT is going to be that different than the control group. We only got a few observations of each one. We didn't have enough to change our beliefs that much. And you can see that if you have a wide enough standard deviation, right, the normal with a mean of 5 and standard deviation of 5, and the normal with a mean of -5 and standard deviation of 5, both actually, since that prior is so wide, it doesn't matter as much where the mean is. The most important thing is what is the standard deviation, because the wide prior is enough to pull it to where the likelihood is more influential. We're believing the data more. We didn't have a strong belief, right? If we have a strong belief, we have a narrow distribution. If we have a wide distribution, we don't have a strong prior belief. We're willing to mostly just look at the data. If we have a mean of 5 and standard deviation of 1, we get something similar to the mean to what the t-test gave us, but we get a narrower credible interval because we already had a prior belief that that effect was likely to be big. So we actually are more confident of that than we were before. The one that's really stands out is if we really had a super strong prior belief that BT would have a negative less abundance in the control, and we put a very, very strong prior on that with a low standard deviation, we get something that's basically opposite of the data. So if you have a very small data set, you actually can, if you have a strong enough prior and not very much evidence from the data, then it doesn't, having just that little bit of data does not change your belief that much because you're highly convinced of this a priori. So that little bit of data is not enough to change it. So hopefully for people that were curious about priors, this helps to illustrate how they really can be influential. Now, this is kind of an extreme example I picked on purpose because it's a tiny data set with only a few sample size. Now, of course, in a case like that, the prior is going to be more influential, and some people would say that's a bad thing, but maybe it should be. We shouldn't make decisions, life-changing decisions that would change, the entire economy of, what corn variety we sow everywhere based on a tiny study with n equals 8, right? In a way, it's good if priors are not influenced that much by a very small data set. So yeah, you want to gather a body of knowledge with many studies, and you can use, so one study's posterior is the next study's prior, right? Like you could use information you got from one study to modify the prior distribution of a subsequent trial with the same experimental design, and then build your knowledge sequentially instead of having to start from scratch with each new study that you do. That's sort of the Bayesian philosophy. Let's see if I have any more slides about that. Yes, and remember that we could do Bayesian p-values, which we learned about at the end of lesson 1. You can also get a Bayesian p-value for each of the posteriors that we got from the 7 different priors. So let's look at what they are. I just included the code to calculate those. So if you just hit Control Enter and run that line, Gathman p-values, and then we'll print the output of that in our console. You can see that the p-value, the p-map is very different depending on what the priors were, right? It's low and close to 0 for the first 2, like we would think, but it's very high for the one where we had a very strong prior belief that the effect would be close to 0. And then it's extremely low for the ones that have a very low uncertainty but are far from 0, if that makes sense. So these p-values are just a way to quantify basically what we see on this plot right here. Does anyone have any questions? Let's go ahead and take a 5-minute break and reconvene at 10 after, and we'll go through at least some of the generalized linear model stuff in the last 4 to 5 minutes, 50 minutes that we'll have after that. So let's take a 5-minute break. I will be right back, and I'll once I get back, I'll answer folks' questions. All right, so in just a minute, we will start back up. Oh, by the way, if anyone is, if Amar or anyone from Stoneville is still on, were you all ever able to connect to Signet?
Yes, Quinton, we did a VPN connection.
Oh, did that
and
work? Oh, that's awesome.
It worked. So
Great.
was
Well,
little
I'm
late,
glad to
but-
hear that.
I was a little late, but it was okay. I'm
Cool.
hearing
Well,
you.
I'm for next week, I will get everything set up so that it will work on Atlas too, just in case, because it's probably a good idea, just in case series goes down for whatever reason. I will, yeah, series actually, it used to be very prone to overheating just because of the way the like AC was in the building where the server was. It would always be overheating, and then the whole server would have to be shut down so that it wouldn't burn itself up. They have fixed that. It doesn't go down as much as it used to. So, but it's probably, yeah, I will put all the files and stuff on Atlas and test out to make everything work, make sure it all works on Atlas too, so you can use that next week if you need to.
Oh, yeah.
But it's good that you were able to get it working.
Thanks.
Okay, so let's continue with the real yes, Alan would like to go over the last figure and how the Bayesian p-values correspond to what's in the figure. Well, you can see that let's do that. So here's the flat prior. The p-value is 0.01, right? So here's that means the ratio of evidence for the null value of 0 to the evidence for the posterior estimate, which is a high positive value. That ratio is very low, so we have higher evidence for this posterior than we do for the null value. So the p-value is low. You could use, 0.05 if you wanted to, a significance threshold. It would be like a significantly different from 0. Versus this one, the p-value is 0.5, right? Because the ratio of evidence for the null to evidence for the observed posterior is closer to 1, right? There is not evidence for a difference from 0 on that one, because our posterior is more dependent on the prior, because we assumed a much tighter prior that had more probability mass centered around 0 and did not allow a high probability of a large positive or negative difference. Therefore, the small sample size we got did not pull us off of that as far, if that makes sense. And with this extreme example of assuming a very high prior probability of a large negative effect and low probability for everything else, we get a very low p-value in the other direction in favor of a negative effect, right? Because we're basically just saying we really strongly believe that there will be a negative effect, and 16 data points is not enough to change our minds on that. That's what that's saying. Does that make sense?
I think so. It's from the graphics. I guess I'm trying to more understand the graphic a little bit. So, but essentially
Okay.
what that's saying is the farther away the median or the mean point is from the 0 bar.
The lower the p-map or p-value will be, yes.
Okay. And so and it's a
Indicating
relative
more evidence for a difference from 0.
for a difference from 0 or for but that's because even though on that last one, on number 7, we had a real tight prior. That's what the second number means, right? Yeah.
Yep.
Okay.
Yep.
All right.
So it didn't
So the prior in that case didn't influence how well we were able to discern that there was a difference between the two treatments.
Yeah, well, it's just the prior, we actually get the opposite, right? So we have strong posterior evidence that BT has a negative effect on abundance, even though the data observed is the opposite of that because of the strong influence of the prior.
Okay. All right. Thank you.
Sure. Yes, keep the questions coming. So we're going to spend the rest of the time that we have talking about generalized linear mixed models, why they're useful, and a couple of examples. I think as we go throughout this course, we're going to get to more complicated situations with different non-normal distributions and different random effects and stuff. The simple models we fit so far, we basically would get the same answer, Bayesian or classical statistics. As long as you put a wide uninformative prior, you're going to get basically identical answers with Bayesian and classical statistics. So why use Bayesian at all, right? Well, as I said, because computationally, they just work a lot better for complex models with lots of random effects, non-normal distribution, fit to small data sets, frequentist, maximum likelihood algorithms can't get the answer. We need the Bayesian approach to actually get an answer at all in many cases. So let's go through a little bit of math or of equations of what a linear model is that we've been fitting so far. This is a general linear mixed model. It's not generalized. It's just general linear mixed model. So what this equation means is that our response y is normally distributed with a mean being a function of the fixed effects and the random effects. X are our predictor variables, like our treatments or covariates, temperature, whatever. And B are our fixed effects parameters, our intercepts and slopes. And then we add on the random effects. Z is basically a matrix that lines up each observation with which group or block it belongs to. And U are the random effects, like the random intercepts and slopes for the different blocks. And it's got sigma, that's the residuals, the noise around this trend. And the random effects are normally distributed. We're saying that the different blocks,
Good afternoon,
some
Alan.
have a higher mean and some have a lower, but they're centered around
well, thank you. How
zero,
about
normally
yourself?
distributed. Yes, okay, so that's our general linear mixed model, right? As I said, the noise around the overall response is normally distributed, and the random intercepts and slopes are normally distributed. That's the models we've done so far that's how they're set up. That works for many cases, right? The normal distribution is a great approximation for a lot of things in the real world, but not all response variables can be fit neatly into that little box. Like what if your response variable is binary? It's yeses and nos, like zeros and ones. Or what if it's a very skewed distribution, like it's a concentration of an element that has a lot of values that are close to zero and a few positive values, but it can't be negative, right? Well, if you fit the model we just showed there, you're not going to be able to have error that's normally distributed. Like the error is not going to be centered at zero with half the error positive and half negative. It can't, right? Because the data are skewed, and so the residuals are not going to make a perfect normal symmetrical bell curve. So that model would not, the assumptions in that model would not correspond to the reality of the data. So it would not be a good model to fit. Not to mention, the predictions it would make would often not make sense. It would make impossible predictions. Like if you fit a model to a bunch of zeros and ones and are like trying to predict the probability of the outcome, if you assume normally distributed error like that, you might get a prediction of greater than 1 probability or a negative probability. That is not a sensible prediction. It makes no sense and couldn't be used. If you fit the normal model to the skewed data, like it's a concentration, you might get a prediction of a negative concentration. That also doesn't make sense. You can't have a negative concentration. Now, we might say, well, we don't care about prediction. We only care about inference of like, is there a difference between the means? But it's still a problem if your model doesn't make good predictions, because if a model doesn't make good predictions, it's not a good fit to the data. And so why would you use a model to make inference about the real world where the data come from if the model doesn't fit the data, right? If you want the model to fit the data, then we can say, well, this model actually has meaning in reality because it fits the data. We can use it to make inferences about how the world is. Otherwise, it just, right, models only exist on our computer or on paper. They don't exist in the real world. We need it to make correspond to the real world for it to be meaningful and useful. Okay, so the data doesn't fit the model. For the old school way of dealing with that is to make the data fit the model, like transform the data and then fit a model to it. Like, let's transform the data in such a way that it is kind of normal and then fit our normal distributed error model to it. That's actually decent, but the problem with that is it introduces bias. Sometimes it's still okay to do a log transformation if you believe that changes in your data are more interpretable on a multiplicative scale. You could do a log transformation, but in many cases, torturing the data to make it fit the model kind of introduces bias. And what we really want is the data is real, the model's not, right? So why are we forcing the data to fit this model that's not even real anyway? Why don't we just get a model that actually fits the data? And that's why people came up with generalized linear models. And so here's the formula for a generalized linear mixed model. Instead of normal here, it could be pretty much any, well, not any, but any of many different kinds of distributions which have a set of parameters, and we call the parameters theta. And now instead of y being distributed along in that way, it's a function of y, g of y. That's the link function. The link function converts the variable from the scale of the statistical distribution to the scale of the data, right? Because we still have this xb plus zu, the fixed effects plus random effects. So if we're multiplying numbers and adding together, we could get any, if you have positive and negative numbers and you multiply and add them together, you can get any number, positive or negative, right? But our response variable, as we said, doesn't always have to be any number, positive or negative. It could be a concentration that's always positive, or it could be zeros and ones. So we use this link function to go from the scale of the statistical distribution to the scale of the data, right? So mapping a value that has to be in this constrained range, like zeros and ones, to something that can be any value. Oh, and by the way, note that random effects are still normally distributed. Pretty much nobody messes with that assumption. Even if we say the data can even if we say this distribution doesn't have to be normal, most people just stick with normally distributed random effects. We're not going to mess with that assumption here, even though it can be done. So let's do an example of that in a Bayesian framework in R with BRMS. Oh, by the way, are there any questions before we go and do this hands-on example? I'll assume you all understood all that perfectly then. Okay. We've sort of talked about generalized linear mixed model. I'll just define those terms. Generalized because generalized means the model can accommodate distributions besides normal. Linear means it's a linear combination of effects, multiplying and adding things together, like multiplying and adding the fixed and random effects together. That's why it's linear. Mixed because it's a mix of fixed and random effects. Right now, we're not going to do the mixed part yet. We're just going to do the generalized part and the linear part. We're going to have non-normal response. It's going to be a linear model, but we're just going to have fixed effects in the model. No random effects yet. It's just a GLM. It's not a GLMM yet. This is an example data set we're going to use. It is also from the Agridat package. The data set is published by Crowder et al. It's a pretty cool natural system. There's a parasitic plant called Orobanche. It does not have its own photosynthesis. It does not produce chlorophyll. It gets all its energy from other plants' roots. And this plant needs a host to survive, right? It's a parasite. So if its seed lands in a soil, it's not, if it germinated without a host, it would die. So it has, it senses chemicals given off by a host plant nearby, and whenever the concentration of those is sufficient, it will germinate. For whatever reason, somebody did an experiment to see how different genotypes of this plant responded to extracts from beans and from cucumbers, two potential host plants. So they had two genotypes of this parasite plant and two different extracts, one from bean and one from cucumber, and did a factorial experiment treating seeds from each genotype with two different extracts to see how many of them germinated. And the way the experiment was set up was they took some number of seeds from one of the genotypes, and some of the plates they treated with bean extract and some with cucumber extract. It was a completely randomized design. There was no blocks in there, so that we don't have any random effects. And the data there was an N for each plate, because for some reason the plates had different numbers of seeds on them. Some germinated and some did not. They counted the germinations, and that variable is called germ in the data set. It's a yes or no. The seed either germinated or it did not. So let's load that data, example data set, and we are going to use the mutate column to compute a new column called P for each plate, germ divided by N, the proportion of seeds that germinated out of the total. And then I'm going to plot it in a box plot. Genotype on the x-axis, that proportion on the y-axis. It's going to be the color of the box plot will be which extract treatment each belongs to, and we're going to plot it with a box plot with a colorblind friendly color scheme. Since I always recommend using that, you never know, a pretty high percent of the population is colorblind, so I always recommend it. Okay, so we're going to load the data, and then we're going to make a column called P, which is germ divided by N, number of germination divided by the total seeds on each plate. And the x-axis is going to be the genotype. The y-axis is going to be the P, the proportion of germination. The box plots will be split up by which extract treatment they got, and each extract will get a different color. And we're going to use a geom underscore box plot. Hit Control Enter to run that. So here's the distribution. You can see that the probability of germination median for this genotype 075, if it was treated with cucumber extract, is about 75% versus, right. So like it looks like, okay, cucumber may stimulate germination more, especially in this genotype here, 075. Pretty basic. It looks like there's an interaction between genotype and extract, because the extract have a bigger difference in one genotype than another. Okay, well, what a lot of people would do is say, okay, we've got proportion data. Our response variable is P, the proportion of seeds that germinated on each plate. Let's just fit a general linear model with P, the proportion, as the response variable. Now, this can actually work in many cases. If the proportions aren't too close to 0 or too close to 1, we can actually assume symmetrical, normally distributed error around that, and it can still work out, because if we're not too close to the edges, that symmetrical bell curve can still fit in the 0 to 1 boundary. It actually can work if you don't have too extreme of data. And we're going to do this. We're going to fit a linear model. P is the response variable. Genotype star extract, meaning we're going to fit fixed effect for genotype, extract, and their interaction between them. And I'm going to put a normal prior with a mean of 0 and standard deviation of 1 on the fixed effect. And this is actually, even though the standard deviation is only 1, think about the units the data are in. All the P's have to be between 0 and 1. So normal of 0, 1 is completely uninformative. It encompasses basically any possible effect size you could have. You can't really have a effect on a proportion like that that's greater than 1. So this is a very uninformative prior, given the small units of our data. So the model formula is P is the response variable by genotype asterisk extract, because we want both both main effects in their interaction. And the prior is normally distributed with a mean of 0, standard deviation of 1, and class equals B, because BRMS uses B to refer to fixed effects, because that is how they are usually referred to in mixed model equations in the literature. Okay, let's run that. We won't look at the output of it yet. That's one way to do it. Now, what I think is a better way to do it is if we instead of using P as the response variable, we actually fit a model directly to the binary outcomes, the 0s and 1s. 0 coding for a seed that did not germinate, and 1 for a seed that did germinate. The response variable, the way you have to write that, has 2 parts. The number of successes, the number of 1s, or the number of seeds that germinated in each dish. And then we have to say pipe or by trials, parentheses, the variable in the data that represents the total number of trials. So that is all the seeds in each dish, germination and not germination. So our response variable is germ by number of trials, which is n. If you go to if we look at the Crowder if you use head of Crowder.seeds in your console, you can see the first few rows of the data. You can see that, right, on plate 1, there was 39 seeds and 10 germinated, right? So that's germ is 10 and n is 39 there, for example. And how do we set up a generalized linear model in BRMS? You have to use the new argument we haven't seen before in a BRM model. Family equals some function of a distribution, parentheses, link equals the link function. Okay, what does that all mean? Well, the distribution function is saying, what is the error in the model? What distribution does it follow? The default is normal. Now we're saying it's following a not normal distribution. And what function are we going to use that is determining the relationship between the observed data and the model predictions? That's the link function. We're going to use family. In this case, binomial is the family and logit is the link. Binomial should make sense because a binomial distribution is a statistical distribution basically that has 2 possible values, 0s and 1s. So just like a coin flip follows a binomial distribution, we're modeling the error in our germination as following a binomial distribution, because it can either be a 0 for not germinate or 1 for germinate. But what is logit? Let's explain what is logit. Logit, right, so we've shown that because we have a linear model, which is made by multiplying and adding things together, fixed and random effects. This term, xb plus zu, the fixed effects plus the random, can be anything from negative to positive infinity. It could take any value. But what are we trying to model? We're trying to model a probability, the probability of germination. Probability has to be between 0 and 1. The logit is a function that transforms this value that can take any value, it's unbounded, into a scale that ranges from 0 to 1. Logit, so logit of a probability is, it's also called the log odds. It's the log of p over 1 minus p. If p is between 0 and 1, the logit of p could take any value. So like as p approaches 1, logit of p approaches infinity. As p approaches 0, logit approaches negative infinity. Here's a graph of logit. You can see that near 0.5, it's kind of a straight line. But once you get to around 0.25 or 0.75, it starts to get steep, and between 0 and 1, or as you get close to 0 and 1, it gets really steep. And the intuitive explanation for this is if you have an event that has an extremely low chance of happening, right? If you're here, a very small increase of the probability makes the odds go up a lot. Versus if you have, if you already, like, let's say you had, you already have a drug that gives you, or a vaccine that gives you 99% immunity to a disease. You're going to need to really work hard to improve on that, right? You're going to need to make, it's going to be hard to improve on that 99%. You can't, there's not really anywhere else for it to go, right? You're already at 99%. The best you can get is 100%. So it's hard to move up on that curve. Versus if the baseline was down here, you could, it's sort of, the curve is shallower, right? It's easier to move up and increase the probability, if that makes sense. As you get towards the extremes, that's where those, right, it's like, eating chocolate changes the odds of, or decreases your odds of getting some rare disease by 100 times. But if your odds of getting that rare disease is very, very tiny, changing the odds by 100 times is not going to change the probability that much. So it's sort of on the relative scale. So we're gonna fit this model again in the generalized linear model. Instead of using proportion as a response variable, we're going to use this number of germination by the number of trials, and we're going to use this binomial with the logit link function to transform our values that can take any number into a prediction on the probability scale ranging between 0 and 1. Now we're going to use a normal prior with a standard deviation of 5 this time because it is on the log odds scale. A 5 log difference is a huge difference. So it's a very uninformative prior because we're saying that we don't know which one will be higher or lower, and we're assuming a pretty decent probability of the effect being between plus or minus 5 log difference, which is a huge difference. So that's a very uninformative prior. And I didn't specify a number of iterations or chains or anything because for this simple model, the defaults are plenty. So here we have germ is our number of successes. And then we have to put trials, parentheses, n being the name of the column of the number of total seeds in each dish. The family is binomial. And the link function is, in quotes, logit, log odds function that we just talked about. And we're going to use normal 0, 5 as the prior. As I said, that is an uninformative prior. And I call that Crowder GLM. It's a generalized linear model. Hit Control Enter to run that. Okay, so let's look at the posterior predictive check plots, the distribution of the data with the model predictions superimposed for each model. And the thick black line in each case is a smooth histogram of the actual data. And each thin blue line is a distribution of the predictions for one random draw from the posterior. We want the closer the blue lines are to the black line, the better fit the model is to the data. We're going to do the PP_check, posterior predictive check plot for the linear model, fit with the proportion as the response variable. What do you see here? Well, you can see that it's reasonably good. We're kind of capturing the shape of it, although the smooth histogram of the data looks like it goes below 0 because of the way the smoothing was drawn, but the data cannot go below 0. But you see the model predictions also go below 0 and are giving us negative probabilities. Doesn't make sense. And if we look at the GLM probability here, you can see these are like the number of germinations in each dish. And to me, this is a better fit to the data. The blue lines are all around the observation. Some are a little higher and some are a little lower, but on average, they are predicting back our data well. So it's a good fit to the data. And so let's look at quantitatively what predictions each of the two models are making. This will help illustrate why the generalized linear model is more appropriate. And the syntax we're going to use is for the EM means function, which we already saw in the previous lesson, is pairwise tilde extract pipe genotype. That means we're going to say, what is the pairwise contrast between the two extract levels within each genotype? So like for genotype, if you look back at the graph of the data, we're going to say, okay, for genotype 73, what is the pairwise difference between the predicted means between these two extracts? And for genotype 75, what is this pairwise difference here? That's what that syntax is going to do. And we are going to do that first for the linear model. What are the means and what are the contrasts? This is the one where we use normally distributed error around the proportion. EM means is the function. Pairwise differences is what we want. We want pairwise differences between each extract, and we want that within each genotype. I'll hit Control Enter to run that. Then first, we'll use the $sign to look at an element within an R object. So we're going to first look at the means. That's the EM means part of it. And here they are. So it says, okay, for genotype 73, the predicted mean is 0.32 versus 0.46. Here, the lower and upper, that's pretty close to what the data here. This is around 0.3. There's around 0.46 there. So that's that. And this is the one for the other genotype. There's a bigger difference as we see in the data. We can also look at the contrasts, the difference in the probabilities, the proportions between the two. So like the difference between 0.32 and 0.46 and its credible interval, and the difference between 0.37 and 0.71 and its credible interval. You can see there's the differences in the proportions and the credible interval. That's how you do it, not in generalized linear model. Now, if we do a generalized linear model, remember that we the model was fit on the logit scale, the log odds scale. So the contrasts are actually log of the ratio of the odds of germination between the two extracts. So we're saying, yeah, the odds of germination in here versus the odds of germination there, what is the log ratio of those two? We're going to do that for the generalized linear model now. I'll go through the rest of this example, and then we'll stop for the day. We've almost finished lesson 2. There's one more example in it we can do next week. I think we should be able to catch up with everything next week. So I've got a few more minutes of stuff for you so you can all get your money's worth here. So we're going to do the same contrasts, except now for the generalized linear model. Still extract by genotype, but now we're using the GLM instead of just the linear model. Control Enter. Then we'll look at the means that the model predicted, the generalized linear model. You can see that they are some are negative and some are positive. That's because these are on the logit scale, and the contrasts are as well. What I like to do, if you have a model with a link function, because nobody knows what this means, like what does the log odds negative 0.418 even mean? What's the actual probability? Well, you can add another argument, type equals response, and that will convert the model predictions from the link function scale back to the original scale. So that's the inverse link scale. That's what we want, and it actually will give us probabilities which are easier to interpret. Type equals response. From that, now if we look at the means, here are the probabilities. So you can see they're quite similar to what we would get from the original model. They're actually on a probability scale, 0.39 and 0.53. And now if we look at those contrasts, if we run this line 137 to look at the contrasts, we have an odds ratio now. So this means for genotype 73, the odds of germination in bean extract is only 0.57 times as high as in cucumber. And the odds ratio is a greater difference for genotype 75. The odds ratio is 0.267. So that means the odds, so like that's about 1 to 4. So the ratio, the odds of germination in cucumber is about 4 times higher than the odds of germination in bean extract for this genotype. Now, an odds ratio, like I said, sometimes people are not as familiar with that, but it's very important for looking at, for interpreting the predictions from models where we're trying to predict a probability, right? It's the ratio of the odds between two groups. If the odds ratio is 1, that would indicate no difference between the odds. And again, since the odds ratios were less than 1, we have evidence that bean extract is less effective at making these seeds germinate than cucumber extract, as we just showed looking at the data again. Now, what if we wanted to do a test relative to a null hypothesis? We can use this function again from Bayes test R, describe posterior. Remember we did the P direction and the P map at the end of last lesson. Describe posterior can basically, it packages everything into one function. It gives you the posterior estimate, the credible intervals, and any Bayesian p-values that you want. So we're going to do that for the linear model, where we just are looking at the difference in the mean proportions, and we're going to do that for the generalized linear model, where we're looking at the odds ratios. We're going to do it for both. And right, just like we are always doing this, looking at the posterior distribution, which is a bunch of samples we took with Monte Carlo sampling. Describe posterior is going to give us the median of that as the point estimate. If we say CI method equals ETI, that means equal tailed interval. That means a symmetrical quantile interval. It's going to give us the 95% interval by default, which are based on the quantiles of those samples that we have for our posterior distribution. And as we showed two different kinds of Bayesian p-value at the end of lesson 1. We're going to use those again, the PD, probability of direction, and the P-map. Next week, we'll review again what the difference between the interpretations of those is, but they're just two different ways of summarizing the evidence for a difference between the means. And we have to say null equals 1 for the odds ratio contrast because the null value for a difference is 0, but the null value for the odds ratio is 1. An odds ratio of 1 indicates no difference. We're going to do this for our linear model and the generalized linear model and see how the p-values differ. Describe underscore posterior. The contrasts from our linear model. We're going to use our ETI interval. And we're going to use a PD and a P-map. PD and P underscore map are our two different types of p-value we're going to get. Control Enter. Here we see the P-map is 0.3 for the genotype 73. There's less evidence for a difference in these extracts versus very much lower for the for genotype 75, and the probability of direction corroborates that. But what if we use the generalized linear model? We will use null equals 1 because the null hypothesis for the odds ratio is 1. What do we get? We get actually lower p-values, 0.05 versus 0.3, and we get less than 0.01. And that's because actually the generalized linear model is more powerful than the linear model because it is accounting for the multiple trials that we had in each dish, right? Like if you had 1,000 seeds and 200 germinated, that's 0.2 proportion versus if you had 10 seeds and 2 germinated, that's still only a 0.2 proportion, right? It's the same, but really we have more confidence when we have 1,000 seeds. The model that's just looking at proportions is not accounting for that. The generalized linear model actually lets you have more power because it's taking into account how many trials, how many individual seeds are in each dish, instead of treating each dish as one value with just one proportion. So it's actually helpful to use the generalized linear model because it gives you more power. The last thing I am going to say about this is you can, if you want to, you could actually look at another level of contrasts. You could look at the difference between, like if you say, okay, we have evidence that this odds ratio is 0.5 and this one is 0.25, we can actually make another hypothesis. Are those two different? Like, is the difference between the extracts bigger for one genotype than another? And this code allows you to do that. It's the interaction contrast because we're looking at basically a contrast of contrasts, the ratio of two odds ratios. And you can do this and then get a p-value and a credible interval for that as well. I didn't put that on the worksheet, but you can just take a look at this, and it's in the oh, I did put it on the worksheet actually. Yes, I did. We want contrast equals interaction, and then we'll describe posterior of that as well. And if you hit Control Enter, you see that. So this is the ratio of the two ratios. So the the effect of extract is basically only 46% as large in this genotype as it is in that genotype. And there's the credible interval. It's far from 1, so we have good evidence that this effect is weaker in this genotype than this genotype. And there's the a p-value associated with that. The last thing I always include, I didn't include this in the worksheet. This is the part I didn't put in the worksheet. This is mainly something that you can look at later if you go back to the text version of the lesson. After each of these examples, I have included a sample methods section that you would put in a manuscript to describe the Bayesian model that was fit and how predictions were made and compared, and what an example figure and table would look like that you would put in a manuscript to go with this stuff. So, and then also how you'd write the results section as well. I won't, since we're running on time and it's not as informative for me to go through this verbally, I'll just say that you should go, if you're interested in this, you should look in the text version of the lesson. This is kind of standard language that I would use for how to describe the Monte Carlo sampling, checking the model convergence, getting the posterior distribution for the different means and comparing them and what different tests you did and that kind of thing. This is stuff that I put in all the manuscripts that I would write with scientists where we do a Bayesian analysis. And results, you sort of talk about what the different point estimates were, and you can put credible intervals in there, and you can put the Bayesian p-values in as well. Say, well, the odds ratio between cucumber and bean extract was smaller for one genotype than the other. Here's the ratio and its interval and a p-value. So you can, that's how I would talk about it in a manuscript. And I also included a figure and a table that you could put as well. I'll just I'll copy and paste the code in the console so you can see what that looks like. Again, I won't go into the details of how it was created, but this is just an example of what a figure showing the model predictions would look like. So you can see here are the median, the black dots are the median, and then I put different credible intervals using different color shading around each mean. So you can see that here are the model predictions. And you can see how the difference for one genotype is much bigger than the other. And again, this jibes with what we saw from looking at the data. And lastly, there's code using the GT package to make a table that you could also put in a manuscript. So again, I'll show you what that looks like if you run that code. You can see here's the germination probabilities for each combination of genotype and treatment, and then the odds ratio, the difference between the two extracts for each genotype. And every time I've put the 95% credible interval in brackets around each one. That's how I'd show it in a manuscript. So that's sort of what I would say are best practices for reporting Bayesian analyses in a manuscript. Okay, so that is the end of that example. There's a little bit more in lesson 2, but it's another just another example of a generalized linear model that we can go through next week. Does anyone have any questions or comments in the last couple of minutes we have? Yes, so where can you find this information? I see in the chat. So yeah, if you go back to the homepage, you can see I have all the lesson text here. If you click on that and go through each section, like this seed germination one we just did, everything we just did in the slides is in here. It has more text that you can read, but then at the end of each section, I've got an example method section, example results section, the figure, and table. So it's all in that text version of the lesson. Cool. Well, I appreciate everybody, or those of you who have stuck around till the end. Thank you. And it's a pleasure. And I will see you all next week at the same time. And I will post the video of this hopefully tomorrow in the same page where I put last week's. I'm not gonna bombard you with emails about that. You can just check that page for the recording if you need it. And I'll go ahead and stop the recording now.